I'd like to thank Berchin and Gail and Ramesh for inviting me to participate. So it's been a really great experience to hear from different perspectives, particularly because I'm coming from electrical engineering. So usually we do not interact even with other engineers like civil engineers and building scientists, and let alone people who are into VR and neuroscience and psychology. So I'm really grateful for this opportunity. And also coming from Hawaii, it is very helpful to understand the perspectives from different settings, different geographies. So I'm going to talk more about a tool that we can use for human building interaction. And so this is more like, we have a hammer and we're looking for a nail, right? So we know how to do this wireless physiological sensing. And human building interaction is one area where we believe this could be put to good use. So just to tell you a little bit about my background, so this is the work that I've been doing with Boric-Lubecke, who is my collaborator and also contributor to my last name, right? So also my husband, and we have been working on this since we were at Bell Labs about 20 years ago. So it's been a long time. We spun out 2 startup companies, so we're now working with Adnovig, which is essentially commercializing this technology for occupancy sensing purposes. So the technology that we use is actually very simple, and most of you are probably familiar with it. This is how you get your parking ticket, or not the parking ticket, the speeding ticket, right? So the police officers, they may point a radar gun in your direction as you drive your car, and they get the speed of your car. And if you're driving faster than the speed limit, you may get a ticket. So what we do is actually using technology that's very similar to that. So essentially we use wireless signals that bounce off of the human chest. They're modulated by the movement of the human chest. And from those signals, we are able to estimate heart rate, respiratory rate, depth of breathing, pulse pressure, heart rate, variability, activity level, position of the person, and so on and so forth. And this is the information that we can use for various applications. So we can actually use this at frequencies that are used for commonly for wireless communication. So 2.4 gigahertz is a very common one. But this can be done in principle at any frequency. So almost down to DC and all the way to light frequencies. So there has been some research with essentially using the same principle using light. So we mostly use frequencies that are used for wireless communications, and the purpose of that, the reason why we do that is essentially we want to use wireless links that are already existing to do this type of sensing. So we normally use signals that are emitted by common wireless devices, and then we use some custom-made hardware that is essentially modulating information about physiology. So the technology is non-contact. It is penetrating through clothing, no problem. We can adjust it for through-wall operation as well. We usually do this at a distance of several meters, but this picture here is showing you some experiments that we have done at a distance of 70 meters. So, in principle, you can do sensing on the moon from here. If you have antennas that are directed enough, if you have enough power that you can send to the moon, distance is not really limited. It's the matter of your signal-to-noise ratio, right? How much signal you have and how sensitive is your instrumentation. So some successful health applications have been the monitoring of respiratory rate. So we produced the first FDA-approved respiratory rate monitor. There is actually nothing that measures respiratory rate in the hospital. Normally, nurse kind of looks at you and then writes down 14 breaths per minute. So if you look at respiratory rates in the hospital, everybody has the same breathing rate, which is 14 breaths per minute, right? So if you're in intensive care, then there are different ways of doing it, but there is really no other monitor on the market that does that. So the other things that we can do is tidal volume measurements, so actually estimating the amount of air that is exchanged. Also sleeping position, which is important for people that suffer from obstructive sleep apnea. So we have demonstrated that we can actually detect obstructive sleep apnea, and what that is absence of breathing despite of respiratory effort. So people that have obstructive apnea essentially what they're doing, their chest is moving, they're trying to breathe, but there's no exchange of air. And if you do this kind of measurement with traditional sensors that are strapped onto the chest, they're just measuring the movement of the chest. You cannot detect it because the chest is moving, but the air is not exchanging. With our sensor, we can actually do it because we're capturing the whole torso area, so we can tell that we have this out-of-phase movement at different parts of the chest. The other thing that we can do is isolation of signatures for multiple subjects. So this is important for sleep monitoring, for at-home sleep monitoring. If we have two people sleeping in the same bed, we want to make sure that we're isolating signatures from two people. And also for, now we're moving to human building interaction and occupancy sensing applications. We want to know how many people may be in the space. And we are also interested in identifying people. So unique identification is maybe not the most correct way to describe this. So physiological signals are unique to us, but there may be a little more difficult to distinguish than, say, fingerprint. But I think if we look at it from the perspective of user authentication, then this becomes a lot more useful. So for example, if I want to know that the person who's taking a test is the person who really should be there, we may be able to do that. If we have a certain population who should be within the building and we know a little bit about them, we may be able to distinguish them from the people that are really not supposed to be in that space. So in a sense, it is similar to the fingerprint that you do need to have some a priori knowledge about the person, right? If I don't know anything about the person, I can't tell who that is, right? So I need to have some physiological signatures recorded ahead of time that would enable me to separate that person from somebody else. So we have used this technology for what we call true human presence detection, also subject count, determination of activity level, and we're moving towards, I mentioned subject identification and also comfort level. So when I say through human presence detection, what that means is really knowing that a human is in a space, as opposed to detectors that are now commonly used for occupancy, passive infrared, that only detect very large motion, right? So the common problem with passive infrared sensors is if we're sitting still, the lights are going to shut off, right? So because of this, a lot of times these sensors are disabled because people get irritated when they need to get up from their chair and wave their hands to have the lights turn on, right? Ultrasound sensors, they also suffer from some false detection, mostly from false positives, so they're very sensitive to air movement. So if you mount those sensors next to the air conditioning vent, for example, they actually get activated when they're not supposed to. So going beyond that, again, as I mentioned, we are able to do subject count, which is very important for, especially for HVAC, to make sure that we actually have enough air exchange for the number of people that we have in the space. Usually the way the spaces are air conditioned, they're air conditioned based on the maximum capacity. So we may have a room that's supposed to have maximum occupancy of 50. You're exchanging air that you need for 50 people, and you actually need to have 10 people in the room. So the big companies that are into HVAC, they're interested in this. They want to know how many people are in space. And it's also, this is important for space utilization, for space planning and space utilization purposes. Activity level, so there is some interest in this area. So if you're in an office building setting, there's probably not going to be a whole lot of difference in how much people move. You know, they're probably not going to be exercising in their office. You know, they may be fidgeting a little bit. But that fidgeting may tell you something about their comfort level, right? If there, you know, there's a difference between people that are, some people may be sitting still and some may be fidgeting just because that is their personality. But that is also influenced by the thermal comfort. So that actually, beyond giving us information of what people may be doing, may give us information about how they feel. And that leads to the determination of how comfortable people may be in this space. So we have done testing of our technology in two buildings on campus. They're They're designed to be zero-net buildings. FROG stands for Flexible Response to Ongoing Growth. So it's a company from San Francisco that designed these buildings. And we have the ability to compare the performance of our sensors to traditional sensors in these buildings, and also at the same time monitor the energy use. And we have some reference sensors for monitoring the number of subjects as well. So this is just showing you some examples of what our sensors can do better than the traditional sensors. So on the top graph, you see that the radar is actually detecting people continuously, and there was a person continuously present in the room, but in this red circle here, the images are blurred for privacy purposes. So we had a reference video camera system that was blurred on purpose, and this was a reference for actually counting people. So, you know, the conventional sensors don't know that a person is there because there's only one person and it's in the back of the room, but we detect it. And then in the bottom graph, you see what's happening, like when you have fans in the room that can actually trip. Ultrasonic sensors think that somebody's there, whereas our sensors can tell that it's not a person. This is showing you an example of a subject count. It's not perfect, but you know we can definitely tell the difference between one person and 10 people, right? When we get into 6, 7, 8, that's a little more fuzzy at the time, although we are working to improve that. So this is showing you an example of activity recognition. So these different segments are showing you mechanical target, empty room, human subject sitting, walking, parallel to the sensor and perpendicular to the sensor. So essentially, based on the pattern, you know, you can have a fan that is essentially oscillating at 1 hertz, right, which is similar to the frequency of the human heart. But it is going to look very different from the human heart. You know, human heart has natural variability in it, whereas the fan is going to look very repetitive. So unless somebody has a pacemaker that's very old, like maybe like a 20-year-old pacemaker or something like that, it's pretty easy to tell a human from a fan. So another experiment that we did is looking at how different sedentary activities show up on the radars. So for example, like flipping pages or fidgeting or, you know, waving your hands and that sort of thing. And, you know, we're able to distinguish those types of motion as well. So the last part that I want to mention is about subject identification. And again, this is a kind of a new area that we're going into. Again, we do need to have some training data for each subject before we can build a model and then apply that model to figure out who is behind the curtain. And we have done this on small samples, you know, so essentially studies with our graduate students. So maybe we look at like 10, 15 people over a course of several months, and we can identify them with a high degree of certainty. So now we need to do larger studies to prove that this is applicable for some practical applications. And the basis for that is, you know, a couple of parameters that we're looking at are respiration patterns. Then we're looking at heart rate variability. So what you're seeing here is essentially how mechanical fan differs from a person, right? So the fan, again, is going to oscillate at a frequency that's pretty constant, whereas human heart, you know, is actually changing the rate at all times, essentially adjusting to your environment, to your physical condition. And then the respiratory patterns, you know, this is essentially showing you, you know, different patterns that we get from people that are breathing with different degrees of difficulty. You know, this is also something that is somewhat unique to different individuals. So we have used several signal processing methods. We have used some machine learning, neural network classifiers, and this is showing you how, based on the respiratory patterns, we can essentially classify people and ultimately identify them. So now the next thing is to move, we're interested in remote blood pressure assessment, so we have had some preliminary results in that area. We're also looking at gesture recognition. We have had some success there, and this is actually something that Google is pursuing very aggressively. And then we also want to move towards thermal comfort, essentially assessing from physiological parameters, you know, what is thermal comfort of the person and how does that affect, you know, their performance and the energy consumption. So the research has been funded mostly by NSF, some by NIH and DOD. And, you know, I look forward to your feedback and possible collaborations. Thank you.